Hello and welcome. Welcome to another evening here at the Linz meetup. We are so glad that you are here and we are excited because today, let me share my screen, is our 30th anniversary. Yes, we can't believe it ourselves. 30 episodes of Linz, and we are a little bit proud and we are super happy that so many of you have joined us on this exciting ride. We had a lot of awesome speakers here at Linz, and we will have 2 additional very nice and super interesting speakers today. But as usual, we are going to kick off the evening with a round of community news. So let me introduce you to what's going on in the Rust community, particularly here in and around Linz. So, a few words about the Linz meetup for those of you who join us for the first time. The Linz meetup is brought to you by the Coding Club Linz. The Coding Club Linz is a volunteering-based community of passionate coders here in Linz. If you are from abroad, Linz is a rather small city right in the middle between Vienna and Salzburg, a beautiful city. So if you ever want to visit Austria, you should definitely visit also us here in Linz. And the Coding Club, as I said, is the organization behind the Linz meetup. Today's speakers, the main figures of the evening. Arnaud will talk about Qdrant, a vector search engine in Rust, and Marcus will tell us how Aleph Alpha is using Rust internally to build awesome APIs. So you see, the motto of today's evening is artificial intelligence in Rust. This is exactly what we want to talk about today. It will not be just artificial intelligence. It will be various topics around artificial intelligence, but I still think that will be a super interesting evening, and I'm looking very much forward to it. So, if you would like to keep in touch with us, ask questions during the talks that I can then take and relay them to our awesome speakers, then you can always use our Discord servers. We also invite all our past speakers and current speakers to join our Discord server, because there you can have a little bit of chat after the evening and ask and answer some questions. So if you would like to join us, feel free to do so. And also, if you have questions around the meetup and so on, you can always use the Discord server to reach out to us. I also posted the link to the Discord server already in the YouTube chat, so you do not need to write it down. Just take a look at the YouTube chat and you will find the link there. Now, community news. And as always, we are starting the community news with our very own Coder Dojo Linz. For those of you who are new, Coder Dojos is our programming clubs for kids between 8 and 17. And we are running one of Austria's most active and largest Coder Dojos here in Linz. The next meeting will be, as every Friday, tomorrow afternoon. Every Friday, we have online workshops, and approximately every 2 to 3 weeks, we also do in-person meetups here in Linz. So if you are not from Linz, but still you have maybe children or nephews or nieces or whoever is between 8 and 17, and those kids would like to learn about coding independent of their previous knowledge, tell them about the Coder Dojo. All they need to be able to is speak German, because the Coder Dojo is German. And and off it goes. We will have a blast tomorrow afternoon using a little bit of coding, learning a little bit of coding. The next one is a brand new meetup that we start here in our coding club together with a vocational college near Linz. It's called Teach to Code. And this Teach to Code meetup is particularly for coding teachers. More and more schools are starting to do programming and coding classes. And we thought that it might be a very good idea to bring teachers together who do coding, who teach coding in schools, in vocational colleges, on university level, but also in earlier stages. And our very first Teach to Code meetup will be on the 14th of March. So if you teach code independent of the programming language, Rust is always welcome. Visit us. Maybe you also have an idea about a great sample that you did for a class or something like this. Sessionized call for proposal is always open. So check out our meetup page. As I said, it's brand new, and we are very excited about this new initiative that we just started. The next one is from our friends at Female Coders. Female Coders is a community of women and girls who are in tech, in IT, or who want to come and go into IT. And Female Coders is offering so-called study groups. And the next study groups here in Linz will be on the 20th of March. Well, to be more exact, that will be a Stammtisch. I'm not sure how to translate that in English, but I think most of you will understand what I mean. And on the 21st March, they will have their next study group. So this is a great community, and I highly recommend to take a look at them. If you are a woman or a girl and you would like to meet other women and girls who work in IT, then you definitely should check out our friends at Female Coders. The next one is another one from our coding club, Linz. It will be the Global Azure Austria. If you haven't heard of this community, it's a worldwide initiative regarding cloud computing and in particular Azure. And all across the globe, in May, there will be 3 days where volunteers run events, local events around cloud computing and Azure. And we will do the local version of it, the Global Azure Austria. We have been doing that for, I think, 8 years now, something like this. And yeah, we are going to do it this year too. We will be in Gather Town this year. So we are pretty excited. That will be something new. And the important thing for this community, Rust is very, very welcome. So if you have ideas about how to use Rust in the cloud, how to use your software as a service product in Azure, for instance, then please send us your proposals. The call for paper is open, and just check out globalazure.at, and there you will find all the necessary information. We are very much looking forward to it. The date is the 12th of May. The next one is another interesting thing. A partner of the Coding Club is Cloudflight, the company Cloudflight. And what they do is they organize regular coding contests. People from all over the globe participate in this coding contest, in the CCC, the Cloudflight Coding Contest, and the next one will be on the 31st of March. If you are here in Austria, you can participate in person if you want, but you can also participate online. It's always super interesting, and it will be a very interesting day on the 31st of March. So check out the Cloudflight Coding Contest. We as a coding club, we engage in this area also because there is also a school edition of the Cloudflight Coding Contest. So if you have, again, kids or nieces or nephews or whoever is in school and they also learn coding, there is a special edition, which is, of course, from a viewpoint of complexity, not as complex, so that students and pupils can also participate. They can participate as a class, they can participate alone, just as they like, and it's open for everybody, and it's possible to join via online. So check it out, Cloudflight Coding Contest. And last but not least, another very interesting event is going to happen on the 10th of March. It's the Meet and Jam. It's a game jam here in Linz. You can participate and build an awesome little game in this event. Check out their website. And of course, Rust is very much welcome. So if you would like to have fun by building a small game with your friends, having fun doing that, check out this game jam, and I'm really sure that that will be an awesome event. So 10th of March, check out the website. I will convert the slides to PDF and send it out through the Discord channel, so you do not need to write down the URLs. Just take a look at the PDF that I will share in the next few minutes on our Discord server, and there you will find all the necessary information. Yeah, and that was it. We are through with our round of community news. And if I check the time, I think I didn't overrun, and I can ask Arnaud to join me on the stage. Hello, Arnaud.
Hey, hi, Rainer. Thanks for having me.
Absolutely. We're so happy that you are here. Let me say at the beginning, thank you very much for taking the time. It's a volunteer-driven program. It's a volunteer-driven meetup here, and we are super, super happy that people like you take the time and join us and talk about their products and their work with Rust. We are really looking very much forward to your talk. Arnaud, where are you based? Where are you broadcasting from?
I'm based in Berlin, so I'm originally from France, but I've been living in Berlin for many years now.
Nice, nice. Berlin, Austria, nice. So we are really international today. Yeah. Great. Arnaud, I think I should share your screen so we get set up and ready for your presentation. We see a
Okay.
beautiful picture of mountains and
It's from Austria, actually.
oh, really nice.
Yeah, it's from Austria. Let me
And
get my
here we
slides ready.
see the presentation, and it seems to work pretty well. Very good. Arnaud, are you ready for your session?
And I think I am.
Yeah, very good. So, to the audience, if you have any questions, always write them in the YouTube chat or in Discord, and I will relay your questions to Arnaud because Arnaud has agreed to do a Q&A after his presentation. We will not interrupt Arnaud, so we will listen to your talk, Arnaud, and at the end, we are looking forward to an interactive discussion. So, thank you very much again for being with us. The stage is yours.
Awesome. So hi everyone, welcome to my talk, which will be about Qdrant, which is a vector search engine written in Rust. So don't worry if you know nothing about vector search engine in general, we'll go through the basics together. So first, who am I? So now you know I'm Arnaud. I'm a software engineer and a full-time contributor on the Qdrant project. My two favorite things are open source software and Rust, so I'm very grateful to be able to work on the Qdrant project. I have myself a bunch of open source projects that I maintain. You can find those on my GitHub profile. And I also have a blog where I write about my projects and about Rust. And I enjoy particularly to write about the performance aspects of developing in Rust. Cool. So the agenda. Of course, we're going to talk about Qdrant, but this won't be a sales pitch. I will give you a general introduction to vector search engines so that you can transfer what you learned today in with other products. Everything's okay. We'll go over a couple of use cases for the technology because good technology without good use cases, not really interesting. We'll peek under the hood, see how it works internally, and by doing so, we'll hopefully see why Rust is a very good fit for the job. Okay, so what is Qdrant? Now you know it's an open source vector search engine, fully written in Rust, and we do embrace the Rust ecosystem. That is, we have a lot of dependencies. We do suffer from time to time from long build times, but that comes with the tooling, I would say. Concretely, you interact with Qdrant via an HTTP, JSON API, or gRPC if you prefer. We have for that 3 official clients, Python, Rust, and Go. It is possible to deploy Qdrant in a distributed setup, which is nice for scaling. But if you do not like to handle the operations yourself, you can use our software as a service. We have a cloud offering so that we'll run and manage a Qdrant cluster for you. To understand what Qdrant does, it's good to have a look at the evolution of search for the past years. Traditionally, search has been about having an exact match on a text keyword. If not exact, then maybe relying on a list of synonyms, or if maybe a fuzzy match with something like an edit distance to have a better match. However, if we look at the internet, we have a growing amount of unstructured data. We have collections of text files, images, videos, audio files, and we have trouble making sense of all this data. Also, if you use the internet, I'm sure you've noticed that all websites now do recommendation. You go on e-commerce websites, they offer recommendation for products. So you want to watch a video, here you go, you should watch this video, you should listen to this podcast, and so on. And this changing trend can be described under the umbrella of similarity search. This is what we're going to have a look at. The easiest example of similarity search is the Google Lens project, which perform reverse image search. Concretely, you take a photo, you upload it on the Google Lens service, and it will first find pictures that are matching visually your photo, but it also give you additional metadata. So in that case, I take a picture, and Google tell me this this picture, this is this flower. So the first time I used this service, I was really blown away, and I was wondering, how is it working? And I don't know, if you think about it yourself, how would you implement something like that? Would you maybe do pixel comparison, which sounds a bit difficult, or maybe rely on some complicated edge detection computer vision library? But I'm not sure this would be as general as what vector search proposes. This was an example for similarity search with a picture, but you can, of course, apply a similarity search to text, and it's called neural search. Here we have an example. We take a subset of Wikipedia, and we're going to query it with what is the capital of the United States. On the left-hand side, we have a classical lexical search, PM25, that relies on keywords, and on the right-hand side, we have a new neural search approach. And we can see that for the classic approach, the first result is the capital punishment has existed in the United States since, then I guess there's a date. And the second and third results are not correct either. So it seems that the lexical search has removed the stop words in the query and has really focused on a couple of keywords. The problem here is that words have different meanings depending on the context. So this really tripped the lexical search approach. Whereas on the right-hand side, we have the neural search. And here we see the top hit is what we want, is Washington, D.C. The neural search has been able to really understand the query in its entirety according to the context. So neural search is pretty good at answering long queries. Similarity search is done by using so-called similarity models. Those models, they are trained via machine learning. There are a lot of models online that you can take off the shelf, websites like Hugging Face, but you have to be careful. A specific model will not necessarily fit your domain. When you pick a model, you have to make sure that it has been trained on data that is really close to what you're doing. The alternative is otherwise to build the model yourself. If the model is large, it can get pretty expensive. For the remaining of this presentation, I assume that we have a working model. Otherwise, those are more machine learning concerned. What is a model anyway? So concretely, a model takes a complex object, let's say a picture, MP3 file, and then it's going to reduce it into a vector. And those vectors are called in the ML jargon, they're called embeddings. And now the secret sauce for those similarity models, maybe a very good information to remember from this talk, is that similar inputs are vectors that are close to each other in space. And here we have an example. We have a query and a document that we both encode using a neural encoder. We have then a query embedding and a document embedding. So those are two vectors. And we are able to compare those vectors by relying on the cosine similarity metric. So cosine similarity, it relies on the angle that is formed between those two vectors to compare them. That's the magic. Here is the first, let's say, checkpoint, a little executive summary about vector search engine. Now we know that those vector search engine, they enable similarity search use cases, like semantic search for text, similar images, recommendation systems. They mostly have two roles. They perform storage, that is, they persist durably vector embeddings, and they enable a search use case, that is finding vectors that are the most similar to an input vector. And obviously, the whole game here is to do those things very efficiently. We're going to make this very concretely with an example that is taken from a blog. Here, the goal is not to look at every line, because we don't need all of those. We're just going to understand what's going on. We're going to use here the Python driver, because this is what most data scientists are using. Here in this first snippet, I picked it. I wanted you to really understand that it's really that easy to load a model in Python using the sentence transformer package. Just one line, model equals sentence transformer, give a name. Now you have a model to work with. Second step is to create a quadrant collection. So the collection is the abstraction that is holding your vectors. That's what you're going to work with. On top of doing the networking configuration, we create the collection by giving it a name. And then the most important is the vector configuration. We have to inform a quadrant of the dimension of our vectors. Here, the size is 384. It's absolutely not a random number. This number comes from the model. The model produces vectors that have this size, so they must be an exact match. And then we also tell Qdrant what is the distance metric we're going to use. Previously, we've seen the cosine similarity. Here we use the dot product, so it's possible to pick whichever distance we want. Once we've created our collection, we can ingest data into it. And the interesting bit is to perform a search. Here we have a search term, and we want to search our collection with that term. And we cannot just send that search term Earth observation to Qdrant. Qdrant doesn't understand strings. It understands embedding. This means you have to encode the search term as well. Then you can send it via this search function on the driver. So the point that I want to hammer here is that the model is necessary for ingesting data, but it's also required for at search time. So this maybe will put some constraint on your architecture. Otherwise, you'll have to maybe pre-compute the vectors ahead of time. Something specific about Qdrant, we are not dealing only with vector, but now you have more interesting use cases. You can attach additional data to your vector. Here on the right-hand side, we have an example where we're going to insert 3 points into a collection we were mentioning. A point is something that has an ID, a vector, and a payload. And the payload is just a JSON object. You can attach additional data that can be used then for filtering. So if you think about it, not only you can ask the question, please find a restaurant that is similar to this restaurant, but you can say, and please make sure that it is within a radius of I don't know, 500 meters from my place. This is pretty neat. We support different type of payload. Here I mentioned geo-coordinates, but we have, of course, text, numbers, and so on. All right, let's dig a bit deeper now. How would you implement vector search yourself? I always ask myself this when I use a tool. And the way you could do it is simply you use a SQL database. You create a table, and for instance, if we have vectors with 4 dimensions, we just have 4 columns. W, X, Y, Z. And you just insert all your vectors in there, and you're done. Now we have a search. What do? We have an input vector coming in. We need to compute the similarity between our vector and each vector in our storage. So we go through the table, and on our way, we're going to make sure to remember which of those vectors has the highest similarity. Then we have it. We can return it to the user. Guess you understood. We just perform the full table scan. This kind of approach can work fine if you have a small data set. I would say between 10,000 vectors to 100,000 vectors, depending on the size, on the dimension of the vector. But quickly, you're going to run into problems here. Generally, if you are doing a database business and you are running into full table scan, you're going to think, I know, I need an index. And we need an index here as well. But we need a special index. So little reminder here, an index is really a structure that is optimized for reads that we're going to build ahead of time to support our queries. Unfortunately, you cannot just use traditional indexes here, like slapping a posting list or a B tree. Fortunately, there are already specialized indexes for vectors. That's not something new. We have the entire geospatial work there. You have indexes like the KD trees, which enable you to do geo-coordinated queries. Once you have those indices, you're able to perform what is called a k-nearest neighbors. That is a search that finds the nearest neighbor to a point. However, you have a problem with those, is that those space partitioning techniques, they are too expensive in high dimension. This is known as the curse of dimensionality in the literature. Basically, all the tools we have regarding algorithm and data structure, they start to break apart as the number of dimensions increase. But we need to handle very large dimensions, so how are we going to go about it? As usual, one way to fix your problem is to relax the constraints. And this is what we're going to do with something called ANN search. So ANN stands for approximate nearest neighbors. And here the constraint we relax is we're not going to ask for the exact precise result. We're going to say, I'm okay if this is an approximate result. So the trade-off here that you're performing is really precision versus speed. Here I have a screenshot that shows you various algorithms, because this is really an active area of academic research. A lot of people are working on this. And you can see on the bottom, it's the precision. I don't know if you can read. You see 1/2, so you have 50% and goes 90%, 99%, 99.9. So you see, we're talking about approximate result, but this is really well over 99%. It's highly dependent on your data set, but this is what kind of precision we're talking about. There are many good algorithms there. Globally, there are 3 categories. You have the tree-based ones, the hashes, and the graphs. For Qdrant, we decided to go with a graph-based algorithm because it's more flexible, and the one we picked has pretty good performance. It's the HNSW one. Now we're going to dig a bit into HNSW. HNSW stands for Hierarchical Navigable Small Words. I'll try to explain it properly. Basically, you have different layers of proximity graphs. So proximity graph is if you are close to each other on the graph, means you are close to each other according to a metric function. The trick here is that we're going to separate the links according to their length scale into different layers. So on top, we have the long links, middle links. At the bottom, we have the short links. This way, we're able to use our graph as a skip list. If you don't remember skip list, you are jumping to a more dense representation as you go down. If you want like a metaphor, let's say you want to travel to the other side of the planet. First, you're going to take a plane, that's your layer 2. Then maybe you're going to take a train, that's your layer 1. And then maybe you're going to take a taxi for your layer 0. Yeah, that's how you think about it. Then you're going to go through this graph performing a greedy search. You're going to take your query. You're going to find the point that is the most similar to your query on the layer 2. Then once you have the point that is the most similar, you're going to go down one layer and repeat this until you reach layer 0, and hopefully you find the best result. So this process is approximate because we do not, we encode only at most m friends, that is m nearest neighbor per vector. And also at each layer, we don't perform an exhaustive search. We only look at EF search node per layer. Of course, you can make M bigger, but it's going to make your graph much more complicated to build. And if you make EF search bigger, means that your search time are going to be longer. If you are very interested in this topic, I can recommend reading the paper from 2018. It's very nice. To talk a bit about Rust, this part is quite expensive, and we use Rayon to make it faster. There is an implementation of HNSW, but we could not use it for 2 reasons. First, the reference implementation is in C++, and also we need to support payload filters. Remember, we do not only look for the closest point, we also want to make sure that they match a specific criteria. This enables many interesting use cases. If you think about it, there are 2 approaches to do filtering on HNSW. You could do what is called post-filtering. First, you go through your index, you find all the similar points, and then from this result set, you will filter them. Now, this has a problem because it forces you to overfetch from your index and then hope that you'll have enough points when performing the filters. The other approach is to do pre-filtering. So first, you're going to go through some kind of index to find all the points that are matching a specific filter. Once you have this result set, you will check which are the ones that are the closest to your input query. So in that case, you do not even use your HNSW index, which is a bit suboptimal, let's say. Those two approaches were not good enough for us. So we have a third approach where we actually enrich our graph with additional links regarding the payload of the indexed points. This approach enables us to perform the search in a single pass, called like single stage search. And that's really one of the key points that makes Qdrant fast. If you are interested in the details of this approach, I can recommend having a look at this blog article. All right, let's go back to the distance metrics. So by now, you should understand that this is a very, very common operation at runtime. We do it a lot during indexing when building this, those layers, and also at search time when going through the graph. We have several similarity metrics available depending on the encoder. That's kind of dependent on your model. That is, internally, we've decided to use a trait to abstract away the concrete metric. This enables us to really split the metric implementation from the indexing and the search. And this way, we can add new metrics without breaking the whole code base. Here, I've simplified a bit the metric trait. The most important function here is the similarity one, which takes as input 2 slices of F32s and gives you, as a result, a single F32. And here the comment is really clear: greater the value, the closer the vector. Let's pretend we implementing our vector search engine and we want to implement dot product that we were using in the previous example. So the dot product, a quick reminder from high school maybe. When you have two vectors, you want to compute the dot product. You can do it by summing the pairwise multiplications. Yeah, that's a simple definition. And here we're able to do it using the nice iterator from Rust. First, we take the first vector. We're going to zip it with the second vector. And as we go down through it, we perform the multiplication. And at the end, we're going to reduce it with a sum. So I really like this implementation. It's a single line. And it will also show that Rust can be a functional language as well. So I called it naive dot product, but I think it's pretty decent. Let's say we ship this and we start doing a lot of search or indexing on it. And let's have a look at how the system responds. You're doing a lot of search. You want to see what's going on your CPU. You start profiling it, and then you find out that 70% of your CPU time is spent into the sum function of the iterator, let's say, infrastructure. If you can see, we can go through the stack, bottom to top. Start at the bottom from our Tokyo runtime. Then we're going to go up our vector storage abstraction until we reach something called HNSW index graph layers. That should ring a bell if you remember what we talked about. And then this is the point where we're going to try to find the points that are most similar to each other by calling the dot similarity routine function that is basically our implementation. So you see this, and so you wonder, is it slow? Well, to be honest, you don't know if it's slow. To know if it's slow, you would need a different implementation to compare it with, right? For now, you just know that this implementation is CPU bound and that it is a bottleneck. And this means that if you remove the bottleneck, you most likely have huge gains. And of course, this is what we did. To do so, we used SIMD. So SIMD stands for single instruction, multiple data. This is those are specific instructions that your CPU can use. And what they do is they apply a single operation to multiple data simultaneously. They're pretty magical in that sense. Those instructions are very specific to on a per microarchitecture basis. You have the x86. For x86, you have the old SSE family, the old AVX, with the latest one being AVX 512. For ARM, you have Neon. Those instructions, they all have different width. The more modern instructions have larger width, which tell you how much data you can stick into it. And as those instructions get better, they get new functions to combine results. There are two ways to use SIMD. Either you hand code the intrinsic yourself, or you rely on auto vectorization from a compiler. To be honest, if you really want to make sure you're using SIMD, you have to hand code it. I would never rely on auto vectorization. Broadly speaking, there are two classes of SIMD instructions. You have the horizontal one, which take a single vector and apply an operation to it to reduce it. So in that example, this is a horizontal add. We add all the elements. Or you have the vertical operations, which take two vectors and apply the operation on a pairwise fashion, and at the end you get a vector. In this example is a vertical add. Now we want to use those, and there's one more decision that we have to make. I said that those instructions were dependent on your microarchitecture. That is, using a specific instruction would make your code non-portable. There are two ways to solve this problem. You could do it statically. That is, you will produce different binaries for each microarchitecture. This is doable, but this will put a lot of stress on your release pipeline. We went with a different approach. That is, we are detecting at runtime dynamically the features supported by the CPU. You can see we have those configuration blocks. The first one is for x86 AVX, the other one x86 SSE. Then we have ARM, and at the bottom, this is our fallback implementation, the dot similarity one that was showing up in the flame graphs. Let's go a bit deeper and have a look at the dot similarity AVX. This is what SIMD code looks like. So first, it's pretty unsafe. Even internally, to make it work, you're going to have to rely on row pointer to load data. In that case, this is AVX2, I believe. We use 256 bits register. Now, the trick that you have to remember here is that we have a 256 bits register, and we're working with F32 float. That is, we're able to fit 8 floats into the register. And here the magic is that we're going to process the dot product 8 floats at the time. The for loop here goes through those two arrays and perform a multiplication addition with the fmadd. I won't go through the details because the code can be a bit tedious. And at the end, we do a sum. We have in that sum 256 register, we have 8 float that somehow we need to reduce, sum, and cast out an F32. This kind of code is not easy to write. You need a lot of knowledge, and I'm really happy we have someone that is very knowledgeable on our team, which makes this much easier. Oh, by the way, this is a simplified version. The real version is called .avx as well. You can find it in our code base. It doesn't fit on the slide, but if you want to go fast, sometimes you have to go dirty. Is it any good? Well, here we have a Qdrant benchmark that compares our dot product function iterator base with the SIMD one. And we use, it's important to be precise here, the data set uses vectors with 1000 dimension. So that's pretty large. and we see a 10x improvement. As we are processing floats 8 floats at a time, we could already expect 8x, and we get a little bit more because we also making the addition a bit faster. When you see benchmarks like that, you're always very happy, but the question is always, how is this performing in an end-to-end system? Now we're going to see how SIMD impacts indexing and indexing benchmark. I took 100,000 vectors of dimension 500, and I've indexed those on my laptop. So let's say the absolute numbers here are not very interesting. It's done on my laptop, and I'm pretty sure I had other processes running at the same time. So we're building this HNSW index with our dot product, and we can compare the two results here. We can see that the dot iterator is above 300 seconds, and when using the SIMD version, we are under 100 seconds. So it's a really great gain. I mean, we basically changed, I don't know, 150 lines of code. You would really miss out not using SIMD for this use case. And interestingly, before using SIMD, we were using the OpenBlast project, which is kind of a reference in terms of speed for linear algebra operation. It's done in C and Fortran. And thanks to the work of the team in optimizing our SIMD operations, we now have similar performance with that project, which is really a great achievement. A bit about the architecture of the project. We said we have a collection that holds vectors. Internally, a collection is composed of several segments, and those segments are kind of created on demand as you add more points. Each segment is independent in terms of storage. We have inside a segment, we have the vector storage, we have the payload storage done independently, and those two are done, are processed within RocksDB. We use the Rust RocksDB binding there. Concerning the HNSW index, we save it in a binary file that we handle ourselves. Those segments, they have a life cycle. They can be full. You need to create a new one. Still, you need to be able to delete things in there. So we have a couple of optimizers that are running in the back that are performing batch deletion, going through the tombstones, sometimes merging two segments together, and so on. Interestingly, when you create a collection, you have to make a choice. Do you want to use an in-memory approach, or do you want to use an mmap approach? That is, do you want to load all your vectors in memory, or you don't have enough memory? Maybe you want to use mmap. Concurrent programming. I think by now you understand that Qdrant is is inherently stateful. We have to juggle with segments, indexes, different storage, and it's quite complex. At the same time, we need to manage the concurrent access on this data. In Rust, you have, like, broadly speaking, two fashion of doing concurrent programming. Either you share data between threads via channel, which is a bit akin to the actor model, where the mutable state is enclosed within threads. Or you do thread synchronizing on a concurrency primitive such as mutex or rwlock. We use both flavor depending on the use case, but we had a lot more, let's say, fun and with the mutex and rwlock. So this is where I'm going to go a bit deeper. Before talking about the rwlock, the mutex protects a piece of data and enforce a single thread accessing it at a time, so it's very strict. If you want to have something less strict, you have the rwlock, which gives you several readers at a time or one writer. The beautiful thing about those API in Rust is that they enforced, the proper usage is enforced by the type system. Here on the right-hand side, this is an example that I shamelessly took from the standard library. You can see there is no unlock method. When you acquire a lock, there's no unlock to do. And this is a bit difficult to understand for people coming to Rust. What's happening here is that when you acquire a lock, if you do a lock.read, you get what's called a read guard. If you do a write, you get a write guard. And as long as you hold this guard, you are holding the lock. Either you need to drop the guard explicitly, or you wait for it to go out of scope to release your lock. The nice thing about this API as well is when you have a lock, a read lock, you can access the data because the read guard implements deref. And the same way, when you have a write guard, you can access the data and get an exclusive reference out of it because it implements deref mute. Those API are really nice. We use a lot of locks in our code base, but we use a lot of locks from Parking Lot, which is another crate that has like more concurrency primitive. They are generally faster and lighter. The problem with locks is, of course, deadlocks. Remember, deadlocks is threads waiting for each other. Here we have thread 1 that holds resource A, and thread 2 that holds resource B, and then they want to access their neighbor's lock, and they will stay like this forever. Another way it can happen is if you perform a double read lock on the same thread, because in Rust, locks are not reentrant, you can run into this issue. I was talking a lot about locks, but you can get deadlocks also with channels. If you start playing around with channels with capacity and cycles, this is very dangerous as well. Those issues with deadlock, they're not caught by Rust-C, and this is sometimes surprising. People expect that all concurrency issues are magically taken care of by the Rust compiler, but this is not the case. This means but avoiding those issues require discipline from yourself. There are several techniques. You could decide to acquire the locks in the same order on all the threads in the code base, or you, instead of reacquiring those locks all the time, you just pass the guards as arguments to your function. Luckily, there are some tips I can give you to help you, because we did have, I would say, a dozen deadlocks, and it's absolutely not fun to track. The first one is to use a runtime deadlock detector. This is a feature from Parking Lot. This is a build feature, so you need to enable it in your cargo toml file. We do it only for our CI build. So our CI build will check deadlocks. And it saved us one time here. We were able to find a deadlock in our cluster status. And when the deadlock happens, you have a really nice stack trace, and it's really helpful. So in my opinion, the deadlock detection is such a killer feature that it justifies using Parking Lot. If you want to go further than this, and you want to try some bleeding edge technology, you can try a static deadlock detector. So this is the project Logbud from Burt and Quinn, which analyzes your code and try to run some simulation to find potential issues in the interaction with the code. We discovered this project because the author just came on our GitHub issue tracker and said, you potentially have a double read lock in your proxy segment. And that was very nice of him. And we fixed it right away. You can use the project yourself. You need a bit of extra, let's say, Rust toolchain tooling, plus you need to compile it with nightly, but it's definitely doable. This project supports the standard mutex, RW lock, and Parking Lot as well. I recommend you have a look at it. Let's go distributed. Having a single node, you can really go a long way with Qdrant. First with Rust, then the SIMD stuff. On a single beefy node, I went myself with more than 30 million vectors, and it was very blazing fast. However, that's maybe not the architecture you want to go with on production. First, you want to stay available. If you have only a single machine, it goes down, you're gonna have a bad time. Also, when you scale, you want to scale on commodity machine. Scaling by hosting only really beefy machine gets very expensive. The way we did it in Qdrant is we have a classical shard replica architecture. When you create your collection, you say how many shards you want and how many replicas. It's a pretty straightforward from a user perspective. We do not have leader shards for write. What we do is you send your request to anyone and we'll figure out where the write should be executed. Any of the replicas can handle a write, and then this write is propagated to other replicas. By default, we do not have transactional operation as a vector. So if you need to support concurrent write on the same points, that's something you have to parameterize yourself by passing a little extra option. We will know that we need to serialize those writes. The way we do it, we had to synchronize some kind of cluster state and have a distributed collection topology. And to do so, we use the Raft consensus algorithm. Quick 101 on Raft. The Raft consensus algorithm enables you to have your node agree on a sequence of operation. This is called your log, and your log has entries, and you want this log to be replicated everywhere. Everyone needs to agree on what's on the log. It's critical. Once this log is replicated, you can execute it. It's a style that is called often the state machine replication. If you have the same state machine everywhere, if they run on the same data, you should have identical result. In Raft, there is a single leader that is elected. And the role of the leader is to receive the proposal for the new entries, send them to the followers. And once the follower act, I've replicated that thing, it tracks it. And when a majority of the followers has replicated an entry, the leader will commit it. And that says, I'm committing this means, follower, please process this entry. Now, it's a common misunderstanding with Raft. People seem to think that this is some kind of atomic global distributed consensus, but you will have basically lags, node lagging behind. So you need to be careful. If you start performing read on your follower, you most likely get stale read, and you have an eventually consistent system. In that case, you need to perform your reads on the leader. Using Raft in Rust, we decided to go with the Raft RS library. This was the most mature library we found at the time. It's definitely not easy to integrate in a code base. There's a complicated, dense to process the message, plus you have to implement your own persistence layer for the log. You have to be really careful there. We had some questions, but luckily the maintainers are very nice and very responsive, so kudos to them. Going in this kind of adventure, when you debugging can be very difficult. Make sure you have good logs and good tests. All right, time to wrap it up here. A couple takeaways. I hope I was able to demystify vector search engine for you, that you know now when to reach for it, what kind of use case it supports. We went through a couple of new indexing schemes to support approximate nearest neighbor and the specific implementation of H and SW. Also, now you know you can apply SIMD to your bottlenecks. If it's possible, you should do it. Here we're doing a lot of float F32 business, but even if you do backend applications, you can parse JSON with SIMD JSON. Just give it a try. Modern hardware is really fantastic. Fearless concurrency in Rust, sure, but except for deadlocks. And this is the responsibility of the developer to make sure those does not happen. Distributed systems are hard. That's not very new, but I had to put it. And basically, this whole presentation is, I guess, another data point in favor of Rust for building concurrent, highly distributed systems. I will leave you with a couple of links. We have first, of course, our GitHub repo, then our documentation, a couple of benchmarks where we see how we fare against other engines, our blog where we push articles about new features and new trend, for instance, now you can start using semantic search for code search. It's very interesting stuff. And the best way to connect with us and the community is via Discord. That's all for me.
Thank you so much, Arnaud. Thank you for this great presentation. It was super interesting, and I ask everybody in the chat. I already saw. I take out your clapping hands and give Arnaud a big round of applause for this very, very interesting session. Super interesting. I could follow. It's not my core area of expertise. I did a lot of database work, but this vector database area is completely new, and you did a great job in giving us a kind of intro in this topic. The first important question that I always get asked by people who watch us, or maybe afterwards who watch this on YouTube, because of course we record everything and put it on the Rust channel. I see the clapping emojis coming in, so Arnaud, everybody is agreeing you did a great job. Are you going to
Thank
share
you very
this?
much.
Are you going to share the slides with us? Either you can put them yourself on our Discord server, or you can also send them to me and I can share it on the Discord server, because you shared very interesting insight into components that you use, and that would be super helpful if you give us your slides, if that's possible.
Yeah, I will export those as PDF. I can host them on my site or put a link on Mastodon, but I can send you a copy as well if you feel better about it. It's fine for me.
Super, very, very good, very good. Thank you very much. If you let me know the URL, I can post it on our Discord server. That is awesome. So people who are watching, we get a lot of clap emojis. That's very good. If you have any questions, ask the questions. My second question would be, it's always interesting for me as a user of such systems to have a choice between self-hosting and using a software as a service solution. And I saw that you have this software as a service solution. You also mentioned it in your talk. Do you run your own cloud, or do you use existing cloud providers? Does customers have choices where to run Qdrant? Can you elaborate on that a little bit?
Yeah, so right now, if you try to create a cluster, you will have only the possibility to use Amazon. But in the future, you'll be able to go in other places. It might be already the case because we're moving fast. But basically, we are relying on other platform as a service, and there we manage our own service.
Very interesting. So in midterm, customers can choose if they are in either Amazon, they can co-locate your stuff in the Amazon data center, and then if they are in Azure, they can use an Azure data center, something like this.
Yeah, definitely. And right now, for sure, I know we have the Amazon. You can pick US or Europe. That's already a given. I know Asia is almost done, and then there will be different provider. So that's definitely coming fast.
Super interesting, very interesting for those developers who don't want to bother with self-hosting. Now we have the first question from our audience. The first question is, how was the Qdrant search engine trained, and what model does Qdrant use for creating the vector embeddings?
That's a very good question. So the thing is with Qdrant is there is no model in Qdrant. You have to ingest your vector embeddings. So you are doing the training. Oh, no, not the training. You have the model. So you are encoding your data and you are uploading those embeddings into Qdrant. And then you can query those. So it's really up to you what kind of model you use for your data. That's why I try to give more information about models, because the model does not live inside the Qdrant search engine. The data must be pre-processed.
So, for instance, if somebody doesn't have so much knowledge about models and maybe use something like OpenAI embeddings, they can just take the embeddings that OpenAI gives them and put them into Qdrant and maybe build a solution on top of that. Did I get that correct?
Exactly, yeah. As soon as you have embeddings, you're ready to go. They can come from anywhere. That's the main point.
Super interesting. Now we have the next question. This is a very interesting one, especially for those in the audience who think about building their own larger development project. The question is, why did you decide to go with Rust? Although you know many libraries not mature yet, was it a big risk? Question mark.
I think it was not such a big risk. I mean, at the time when the project started, you basically had the choice between C++ and I guess nothing else. Now you see that there's a lot of computation going on, so you have to pick a runtime that is extremely fast. C++ is a language that has a couple of foot guns, I'd say. The project is rather young. We started 2 years ago, so Rust was already in a good shape. So yeah, it was mostly about, are we ready to do the HNSW implementation and so on. And given the knowledge that was in the team, the trade-off was, we have the knowledge, we should go with a language that will support us on the long term and where we will be able to hire great people.
Yeah, very interesting. Very interesting. Thank you very much. I would like to follow up with one question that I sometimes get asked by students when we talk about different databases and vector databases. When does it make sense to use a vector database like Qdrant for an artificial intelligence solution? I mean, I could store my vectors simply in files or whatever. Do you have some size indications? Is Qdrant only something for very large projects with thousands of, hundreds of thousands, millions of vectors? Where is this break-even point? Does it make sense for a mid-range or smaller project?
So that's something I've covered when trying to implement a vector search engine using a SQL database. And here I said that you can rely on a traditional data store, as there's a sweet spot, let's say. It's between 10,000 and 100,000 vectors, depending on the dimension of your vector. That is like 10,000 vectors of dimension 1,000 are really not the same business as 10,000 vectors of size 200. So you have this 10,100 depending on the dimension. If you go above, you most likely need a specific solution that is really tailored for this use case. As long as you have small data set, yeah, you can get by with a full table scan, I would say.
Yeah, very interesting. I think if I can remember correctly, the ADA model from OpenAI produces 1,500 dimensions, something like this.
Oof, that's pretty big.
Something like this. Yeah, I think that is on my mind. I see additional questions coming in. Arnaud, I don't know if you are in Discord. If you are, we invite you to join a Discord server, and maybe you can hang around there a little bit. Or maybe you can send in the YouTube chat your email address where we can contact you, because I think we have to move to our second speaker of the day, and I hope that is okay for everybody. Again, big round of applause for Arnaud. Thank you so much for sharing this super interesting information. And with that, I think we should quickly take Marcus to us. Hi, Marcus.
Hello.
What do you think? Didn't Arnaud do a great job in his talk?
He did do a great job in his talk, but actually there were multiple touching points. If I was tempted to change my slides on the fly, I tell you.
I'm sorry.
No. Don't be sorry. I like it. Right. Remarkably, there were some touching points you will see. Right. And also with the questions, I can refer to that.
Super.
I wanted to add more content on the fly, but I can do so in audio.
Very good. So with that, thank you very much, Arnaud. Thank you for joining us, and have a very nice day. Greetings to Berlin. Bye, Arnaud.
Yeah. Thank you for having me. Ciao.
Bye. See you. Marcus, where are you broadcasting from?
Oh, I'm broadcasting from my home in Darmstadt, which is close to where I work, or reasonably close to where I work at Aleph Alpha in Heidelberg.
I see. Very interesting. Marcus, also, I would like to take the opportunity to say thank you. This is a volunteer-driven meetup, and we know everybody is busy, and we value that very much, that you take the time to share some information with us, being with us with this artificial intelligence and Rust evening. Marcus, are you ready for your presentation? I think we can take your slides on the screen.
I think it would be a bad time not to be ready for my presentation, right?
So. Exactly, that's it. Marcus, we are looking forward to your talk about Rust at Aleph Alpha. Thank you very much for being with us, and the stage is yours.
Yeah, so hello, I'm Marcus. I also like to do a lot of open source work, so my GitHub handle is pacman82. Most of my open source work happens in Rust, and I think my most meaningful contribution is probably the ODBC API binding. So ODBC is for accessing databases standard, and I maintain the bindings for Rust for it. So data engineers might also know my ODBC to Parquet tools, and there's a few other grades, but I won't go in there. Personally, I've done most of my career as a C++ developer, but I'm using Rust since 8 years, roughly before it became stable in version 1.0. And currently, I'm the head of engineering at Aleph Alpha. So what do I want to talk to you about today? For once, I want to talk to you for what we use Rust at Aleph Alpha. And then I want to drill deeper into two specific problems, which also spawned the creation of two open source crates. And I want to share the problem with you so that you might know how to pick them up or improve upon the solution. Okay, for that, I need to provide you with a moderate amount of context and a little bit of advertising. What we are doing at Aleph Alpha, we are striving to create sovereign European AI. We are targeting enterprise customers mostly, but any private person can go to that link, use our playground and use our product or use our API. So one question I want to elaborate on from the previous speaker was where to get the embeddings for the models for the search engine. Well, OpenAPI is one step, but you can also get them from Aleph Alpha. So just to elaborate on that. However, what I've prepared here is a different kind of task, not an embedding task, but a completion task. With what you see here is a slightly younger version, both of our UI and myself. And this is a completion task based on a multimodal prompt. Multimodal, because there are two modes of input here. One is text and one is a picture. And the model is trained on text. And what it will do, it will complete the text. So it will just continue writing the text. And the text is phrased as question, Q, and then there's an A for answer. So the model is primed, okay, now probably there should come an answer to that question. And before the question, there's a picture. And so that results in the completion, a man with glasses and a beard, which is a reasonably accurate description. And this I will use to explain what we do at Aleph Alpha. So how does Factor Rust into it? So at Aleph Alpha, we are a fairly young company. So there has never been, at least from my point of view, an Aleph Alpha without Rust. I was hired via the Rust newsletter. That's how I discovered the company. And so I cannot tell you a tale, oh, this is all the production errors we had, and when we switched to Rust and all went fine. In that regard, it was always fine. What I can tell you, though, is what we are using Rust for and what we are not using it for. So what we are not using for is the core domain of AI and natural language processing itself. So Python just looms large here with PyTorch and all these fancy bindings, and it's just very much loved by our researchers, and we wouldn't take it away from them. Also, the prototypes, quick POCs, are usually also done with fast API and Python. What we do in Rust, though, is inference preprocessing. So inference is the process of actually using these models in production. And what the user sends is not quite what goes into the model. So all this text has to be converted to numbers in various ways. But Rust is very well suited for this job. Also, data pipelines, these models are trained on large amounts, terabytes actually, of data. And there's a lot of pre-processing and command line tools or stuff that goes into which does it, and it's reasonably fast doing it in Rust. And yeah, basically, if it's done by the engineering team at Aleph Alpha and there's no good reason to use another language, it's usually done in Rust. and all the boring stuff we do in Rust. And the nice thing about it, so that's not as negative to me as it may sound, it stays boring. Like doing a lot of DevOps and operations, right? Boring becomes a pretty positive term. And in short, I could summarize it that we use Python for fast idea iteration and we use Rust for production. So somebody wants iterating over ideas fast. He doesn't want to be bothered by, oh, what would happen if that would go wrong. He just wants to move on to his next plot, to his next idea. And in Rust for production code, I actually want to be buffered with everything that could go wrong. And this design is actually not quite right. Please think about the ownership model again. So that's roughly how I decide what to use. We, of course, use TypeScript for everything UI. No argument here. Another thing that I found interesting was hiring Rust developers. It turned out that I thought this would be hard, and in a sense, I was right. But the last 3 developers which were hired, they didn't use Rust before at all, but still in their second day after their commits from them were already running in production. Pair programming, of course, helps a lot with this. But I reasonably cannot see anymore that Rust is hard to learn. People can pick it up really, really quickly. What is actually hard to learn is maybe ownership model or software design, but these were concepts that existed before, right? And a C++ programmer who understood ownership, he can just pick up Rust really quick. And yeah, so for me, I would say hiring Rust developer is hard, but Rust doesn't factor into it because I don't hire Rust developer. We just hire good software engineers, and that was always been hard. But previous knowledge of Rust itself is not required. They pick it up all fairly quickly. Okay. Moving on to the open source grades, which have been spawned by little problems we had at Aleph Alpha. But one honorary mention must go to the Aleph Alpha Rust client, right? So the majority of our features is actually covered in the Python client. The Rust client is more like a spare time, rainy day project of myself. Everybody's invited to contribute. It doesn't cover the entire API by far, only whatever I need in that moment I add it. But embeddings are in there, and here is a code sample for completion task. Basically what you've seen in VI before, just with a cat picture instead of a picture of me. And the first problem I want to talk to you about is waiting on external events. So for this, I want to share with you a little bit of an architecture slide, a block diagram. So we have here a user want to send his completion or embedding task. He can use various means of it for this. But ultimately, a request reaches our API. And now the API does distribute these tasks to a worker. However, it does not send a request to a worker and get an answer. Instead, the worker fetch these tasks batch-wise and answer them batch-wise. So what does this mean for the control flow? A worker might ask for work. This is just one example of how it could happen. And when a user sends a completion task, the API does a bit of work and answers the worker's request for work, because now finally there's work in the queue. And then the worker answers with the completion. And now we want to send the completion to the user. Okay. Why is this a problem? What could be a bit of a problem? Let's consider a code sample. And in this code sample, I switched to architecture a bit. Now I just have a worker, which is a service. I send him a completion task, and I await the response. And now I can simply wait for whatever result I want to have in the handler of my service, and all is good. So, but that's not actually what we do, right? Instead, I have a user calling a completion route, and at one point in time, a worker will kindly give me a result to the task, and now I have to do something here so I can wake up here. And the question is, what do I wait here? What is the future I'm awaiting? And it turned out to me that I already solved these problems some time ago. This is the README of a throttle semaphore server. A semaphore is a synchronization primitive, like a generalized version of a mutex. And this is throttle is a semaphore service for a distributed system, not itself a distributed system. This is important distinctions, but usually that's what you want. People always ask for distributed mutexes, but they want actually a mutex for a distributed system. And actually, it has a deadlock detention by enforcing lock hierarchies. One of the touching points to the talk earlier. And if we look what throttle does actually, well, it has to have at least 2 clients, so it's fun. So we can wait on each other. And then let's say, okay, client B starts, asks for a mutex and acquires a lock, and then keeps busy with the lock. Meanwhile, client A asks, but throttle will answer him right away, okay, you don't get it, or delay that answer. And after a while, client B releases the lock, and then it gives the acquired lock to client A. And this second part of the flow diagram, the part how we answer and what we would wait for in the handler, that's exactly the same. And so I extracted that part out of throttle into its own ASIC events crate. So the name, actually, I don't like it, which is probably a hint I don't fully understand what I did here. But at least it served me well on 2 occasions. So I thought I might just share it with everybody so it could be useful. And remarkably, once I extracted it, I discovered, okay, it depends on nothing, right? I don't depend on TOC.io or standard async or anything. It's completely independent of the environment, which just, I think, goes to show how smart actually the Rust async await system is designed and how well the execution is separated from the usage. I was really remarkably euphoric about that, although I only use TOC.io. So how does it help us with our problem? Well, I could introduce a little struct, neatly also taking some of the domain logic out of the handlers, not following the smart UI anti-pattern, and just an ID, so every task gets its own ID, and we can identify what answer belongs to what task. And when I introduce async events, you can see here the structure is generic, so I could basically do any kind of result, including Rust results to transmit errors, and also the ID type I want to use to identify the event. And then I give it 2 methods. So on the completion route, which is basically the sending work route, I get, of course, the prompt, which is the input. I generate an ID. When I need to send the work to the worker, I will omit how we do that. All the queue stuff is now not interesting for this. And then I just wait of the output of that event. And then I need another route, which tells us the result. It tells us which ID it's for and the result itself. And here, one of the observers waiting for it will be woken. And that allows me to go back to my handlers and wait simply on the result of the completion. And when a worker reports a result, simply tell it about it. The second artifact, which is also is called log hierarchy. So personally, I'm a big fan of the actor model. And usually the fix for me is actually to switching to the actor model because all the state got too confusing. But sometimes you just say, okay, we don't have time for that refactoring, or sometimes actually not choosing the actor model is the right choice. And then you have the aforementioned deadlocks. And also we had them. And indeed, Rust does not protect them from them. It only protects from not even all race conditions, just data races, but that's actually quite a lot already. But what I decided to do was not to search for actually detecting deadlocks at runtime, just catch it one level earlier, detect any violation of the log hierarchy. The fun thing there is it becomes quite deterministic. And I have even a little demo prepared for that. So in that case, no realistic demo, just one of these academic examples, probably the most academic examples of them all, because it's about philosophers sitting around a table. Each of them has a fork to its left and its right, and they need both forks to eat. And once they have eaten a bit, they lay down the forks and go back to thinking, and then they start eating again. And the interesting thing here is, of course, it's a shared resource because basically each fork can be acquired by two philosophers. So now I will do maybe switch over to my Visual Studio Code in the screen sharing. Let's see if I stop the screen sharing. Present. Share screen. Share screen. Select window. I hope my, it seems like my editor can be seen. Let's create a new shell and let's go to the philosopher's example. I think it's from some older version of the Rust book. I modified it slightly so the philosophers will start the eating thing over and over again. I just run it. And we see here some output. There are 5 philosophers sitting around a table. They all eat. And at one point, it just stops. And that's due to a deadlock. And what I do want to do first, I don't want to fix the deadlock. I just want to find the deadlock way earlier. And for doing that, I just use log hierarchy here and replace the standard mutex with it. And that basically makes every mutex on the level of 0, which means no 2 mutexes can be acquired at once. That means it will fail right away, pointing to me to a line in its error message where the mutex is acquired. So now I get a deterministic error, and I don't even have to wait it for running a long while to see that there's something wrong with my product. What I now can do is I can give each mutex a level. And acquire it in order. That should still crash, just assigning them levels will do nothing. But now, if I acquire them in order, that should fit the bill. It should. That's why you practice your demos earlier. I think I may have switched around how these work. Yeah. Okay. Now back to the slides. I just want to thank you all for listening. There's still some positions for Rust developers open on my team. So if you want to check it out, here's a link. And I thank you all for your attention.
Super interesting. Thank you very much, Marcus. Thank you. Everybody take out your hands, give Marcus a big round of applause. Marcus, there were really a bunch of connection points with the first talk, especially when it comes to deadlocks and so on. Super interesting. I think that many of the things that you just told us are not solely applicable to artificial intelligence applications, right? So essentially what you do, or it could be applied to any system where you have a kind of API in the front end and any kind of worker-driven backend that asynchronously does some workload. Did I understand that correctly?
So yeah, the async event crate basically is waiting for external events that may occur in all kinds of distributed or non-distributed system. But since it waits on events that are not within your process, it's probably a distributed system. And log hierarchies, this is just a little crate, right? It's not even, I think, 100 lines of code, just enriching the standard mutex a bit as a drop-in, right? You could do way more with that. But of course, logs you might have in any kind of concurrent code.
Yeah, first, it's awesome that you share these things with the community by making those work open source. That's a great thing. People in the audience, if you have any questions to Marcus, keep them going. Otherwise, I will start with some questions. One thing where I'm not 100% sure if I got it correctly, imagine for the async await stuff, you have a lot of workers in the background. That is obviously some kind of worker farm. And if you have the web tier also distributed across a farm of web farms, something like this, how is the network communication done? Is this a part of async events, or do I have to plug in my own routing system, or how does this work?
So you mean if not only the queue giving the badges to the workers, but also I think answering requests is yeah, it's actually it's actually worse than that, right? So it's not part of async. We have actually several layers of these events, because there's actually a many-to-many relation in reality between what a user sends us and what a worker receives. So we might batch multiple requests for user and go in one forward pass through a model for efficiency, and ultimately one ask for a user might also result in several tasks. So there's actually more layers in between there. So once we have intermediate results, they might be aggregated again. They might spawn new tasks which needs to be distributed to the workers, which and aggregated again. And once we have a final result to the user, we just send it. But that's pretty straightforward. So there's no because when you have a one-to-one relationship between what the user asked for and what you send, and then you can just make it also a service.
Okay. Got it. Marcus, your slides, I think they were on Reveal. Do you share, or is there a possibility that you share your
Yeah.
slides with
Yeah.
your
Slides
community?
is a bit fancy, right? It's a markdown,
Yeah, that's
which I
fine.
write
That's
with some
fine.
separators, and I'm sure. I'll give it a copy to you, send it to you.
Oh, that's very good, because then I can share it in the chat of Discord, and people who are interested in using your open source crates, they can take a look at and find find the link there, or find the name there, because maybe in a few months somebody has exactly that problem and can't remember the name of the crate, and then they can go into the Discord server, check out your slides, and then they remember, this was this async events crate that Marcus was talking about. That would be super interesting. If I don't see any additional questions currently coming in from the community, anything final words from you, Marcus? Any comments that you would like to give our to our viewers?
No, I'm just really thank anybody for listening, and if you have any questions, or want to use these artifacts, raise issues, I always welcome contributors. My time is spread a bit thin recently, but I'm always happy to share and contribute.
Super interesting. I personally find it very interesting to have companies like Aleph Alpha doing a lot of contributing a lot of work in the artificial intelligence space. Of course, we have here at Rust Linz also some viewers from the US, but we are a Rust meetup based here in Europe, and it's awesome to have a company like yours doing work in Europe and doing artificial intelligence work here in Europe. And I can imagine that you have a lot of work at Aleph Alpha, building a great API front end, just as you described it today. You're doing an awesome job. And I think this was a nice combination of the search engine on the one hand side and your software that can generate the embeddings. And with that, I think, I have to thank you again, you and Arnaud, for joining us for this evening. Marcus, with that, I would like to say thank you. Thank you for joining us, and many greetings to, was it Darmstadt?
Darmstadt.
Darmstadt, very good. So enjoy the rest of the evening. Thank you for joining us, and I hope we will see and hear from each other again in the future. Marcus, have a nice evening.
Bye, Rainer.
Bye. And that was it. That was our Rust Linz meetup for the day. I hope it was interesting for you. We tried to put together two interesting topics around artificial intelligence and Rust. If you have any questions, the best thing to get in touch with us is through Discord. Send us a direct message or use the Discord channels that we have there. And with that, I would like to wish you all a beautiful evening, and we will see each other in approximately a month. We are currently putting together the agenda for our April meetup, so stay tuned, join us on Meetup, and we will make sure that we inform you once the next meetup comes up. So have a nice evening. That's everything we have for you today. See you next month. Bye.